Hello, my name is Andreas Schindele. I'm from the University Hospital of Augsburg. Unfortunately, I cannot be there at the 2nd of October, so for you today, that's why I'm recording this tutorial now. The tutorial is about the coffee break script. You've seen that there are a lot of steps included in the SPM analysis for patients with disorders in consciousness. And luckily, Ariana Sala and me, we have implemented a script that is doing all these steps automatically. I first want to give a short recall about all the steps that are included in this SPM analysis, and especially the steps that are done by the script. So first, the script is automatically set an origin point close to the anterior commissure. So you can see it here. This origin point is necessary in order to do the registration and the normalization that is done in the next step. This is step 2. First, the image is co-registered, which means if you have them like this, two images, you want to translate it and rotate it such that they fit to each other. And then the normalization can be done, which is warping the image such that they really fit to each other. In a third step, the algorithm is smoothing the images with a Gaussian filter. This is done to reduce the noise of the images. The fourth step is the heart of the SPM analysis. This is the statistical comparison of the smoothed image that we just calculated with the healthy controls that we have. It's 33 healthy controls and they're compared. And then we obtain the relatively hypometabolic and relatively preserved areas with a statistical significance level of 0.05. Then we come to the outputs that the script is providing. First, it creates Excel lists. These Excel lists display the hypometabolic and preserved regions in all the regions of the brain. And we will see this later. And it also calculates a normalized SUV image, this standardized uptake value, and we can compare this with a mean SUV image from the healthy controls. And in the last step, also the different brain slices are calculated, and in these slices the relatively preserved and relatively hypometabolic regions are shown simultaneously. What are the requirements for the script? We first need MATLAB because it's implemented in MATLAB, and also SPM is implemented in MATLAB. And we need at least the version from 2019. And we need the SPM software package, which can be downloaded from this link. And then we need to add the SPM path to the MATLAB path, such that MATLAB can find the SPM scripts and the SPM code. And of course you need the script implemented by us, the coffee break FDG-PET script, and the healthy controls and an image template. And if you have all this, you can run the script and enjoy your coffee break while the script is doing all the work. Now I want to show you a bit about how to run the script and what is important to look at and the outputs of the script. And first, as I already said, we need to include the path. So for this, we have to go to Home, here Set Path, and then Add with subfolders. Now we have to find the SPM path where we have it. I have it in SPM project, SPM 12, and we just include it, add it with all the subfolders, and then save, and now MATLAB can find the SPM that is necessary for the script. Then I want to shortly show you the file structure that we have. So here is the main script, coffee break FDG-PET, and then there are some subfolders with some subscripts. For example, here the subscripts, this is doing basically all the steps that I've shown you right now. First, it gets the DICOM information, and then it sets the origin automatically. This subscript does the co-registration, this subscript does the normalization, then these subscripts do the statistical comparison, and here the F, they calculate the Excel files for different regions and different language areas of the brain. And this one computes the SUV image, and this one normalizes the SUV image. And at last, the SUV image is saved in the range that is given, and where we also provide the healthy control mean image with the same range, so that they are comparable to each other. And then the absolute values are comparable to each other. Okay, then we also have here our masks. Here are the healthy controls, and here is a template image. And yeah, then there are some other functions and some job files that are also used by the subscripts. Okay, so there are two different possibilities to run the code. We can, when we have the code in the editor, we can go to editor here and click here on run. And another option would be to just write the code here, so we can make coffee break FDG-PET. When here we are in the correct folder, such that it can find this script. So now I'm running it. I first need to define the patient that we want to look at. I want to look at the first patient, for example, and here the CT-AC, which is the attenuated correction from the CT. Here you can go into the folder on the left side, and on the right side you can choose a folder. Here we chose the folder with the DICOM files in it. And then we press done, and that's it. Now all the rest of the job is done by the script. So here it first imports the DICOM images, DICOM header also. Then here it does the co-registration. Here we see the co-registration is done. Now it did the normalization with this, there was the formula how it was normalized. Now it does the statistical rendering, statistical comparison, and now for the preserved areas the same. Here is the slices. I will show you all the images later. Okay, and now it's the SUV was calculated, and now it's done. So I will close this first. So now for the quality control, as you've seen in the talks before, we first want to have a look at the mask to see what the algorithm considered to be brain and what he didn't consider to be brain, if this is reasonable. So I open MRI cron. Here you can read MRI cron is a viewer for nifty images, for example. So I will open the David Bowie patient, and we want to SPM, we want to see the mask. So I open the mask. Okay, so here we can see the mask. He considers to be brain what should be brain. Here there is something missing. Probably there was the brain was so hypometabolic, so low information that didn't consider that to be brain. So we have to be careful that even if this can be hypometabolic, it will not be shown as hypometabolic in our calculations. And as a second step, we can see if the co-registration worked well. So I again am opening, go to SPM, and this can be seen in the should be seen, or was it here? Ah, here, yeah. Set origin correct. I open it, and here we can see it. We see, okay, here the origin was set quite well, and also the images are aligned. On top we see the template image, and here we see our aligned image, and I would say it is well aligned. And this third thing for quality control that we can check if the normalization worked well. For that, again, I would open here the template image, which can be found in the subfolder mask templates that I've shown you before. On the bottom, here is our template image, and I will also open our calculated image. Yeah, David Bowie. First, only normalized without smoothing, and we also have the smoothed one, which is more comparable to the one from Healthy Control. And we see, yeah, again here there is something missing because it was not considered to be brain, but they really resemble to each other. And yeah, I would say normalization worked well in our case. And then we can have a look at the outputs. First, we can see at the Excel list. Here we see all the regions of the brain, the left presental, right presental, and all these regions. And here we see the percentage of voxels in this area that are hypometabolic. For example, in the left precentral region, there are 9.6% of the voxels hypometabolic, and 41% rounded are preserved in this area. And if we have a look here, for example, the left fusiform, almost all the pixels, 98% are hypometabolic. So in this region there is not much information, not much activation anymore. Yes, so and another output are the renders. There are usually the old renders are used. In our case, they look like this. So here we see the hypometabolic areas, and also here in this area we see, because here it is really hypometabolic, but then it suddenly stops, and this is because this was not considered as brain anymore because it was too hypometabolic. So we have to consider this in this case. And there is also a new rendering that the script is providing, which looks like this. Yeah, it depends what you prefer. Usually we use the old one. And the preserved areas can also be shown here. And there's also the multislice display. We can also display the brains in a multislice way, so all the slices of the brain are shown here, and we see in the warm colors, in the hot colors, again we have the preserved regions, and in the cold colors, green and blue, we have the relatively hypometabolic regions. Okay, and at last I would like to have a look at the SUV image, which is here. So this is the SUV image in a range from 0 to 12, and we also have a mean image from all the healthy controls in the same range for the SUV. And I have it, where did I save it? Ah, here, yeah. So yeah, so we can also compare these two, and we see this is lower, especially here there is a lot of red missing, and so we can directly compare the absolute values to each other and see yeah, how much is the activity reduced, or is the information, the PET, FDG-PET information reduced. Yeah, that's it for the script. And a small outlook, what we still plan to do, our future plans. We want to also automatically create a clinical report, including all the results that we provided, excluding the anatomical report. This has to be done by hand. And we want to set a pipeline for pre-processing the healthy controls. We also want to include alternative quantification metrics, for example, the metabolic index. And we want to set a pipeline for including different image modalities, such as structural MRI images or functional MRI images. Yeah, thank you very much. That's it from my part. And if you have questions, you can ask them to Ariana Sala. Thank you.